Hi, I'm Ms. Roger, and welcome back to Core Concepts in Algebra 2. Today's lesson is on logarithms and exponential functions. Today's lesson is tied to the Massachusetts Curriculum Frameworks for Mathematics, specifically FIF, Functions Interpreting Functions, number 8, and F-BF, Building Functions, number 4A, and FLE, Linear, Quadratic, and Exponential Models, number 4. Let's take a look at today's lesson objectives. To rewrite equations in exponential form in logarithmic form, to condense and expand logarithmic expressions, to evaluate logarithmic expressions in exponential expressions, to use the change of base formula, and to solve logarithmic equations using properties of logarithms. Let's take a look at some key points. Any function of the form f of x equals a to the x, where a is greater than 0 and a doesn't equal 1, is called an exponential function f with base a. If b is greater than 0 and b does not equal 1, log base b of y equals x if and only if b to the x equals y is called a logarithm. This is read as log base b of y. Think about this as what exponent do I raise b to in order to get y? This is going to help us as we start to solve problems. And another thing that we want to consider is that a logarithmic function is the inverse of an exponential function. Let's take a look at some terminology. Common logarithm is a logarithm with base 10. This is written as log base 10 of y. Since it's a common logarithm, we typically don't write in the base 10 since it's assumed, and we would just write log of y. For a natural logarithm, this is a logarithm with base e. This is written as the natural logarithm base e of y. When the base is e, this is usually not written in or included in the logarithmic form, so it would just be denoted as the natural logarithm of x. It's important to note that if we have any base other than 10 or e, it must be written in for our problems. Let's take a look at an example. 2 to the 4th equals 16. So this is an exponential form, which maps up with our notation here. If we want to write this in log form, this is going to be log base 2 of 16 equals 4. And again, we can go back and forth from exponential form to log form and log form to exponential form. This is something we want to get comfortable with through our work. So another example for natural log is going to be e to the x equals y. And the way that we would denote that and write that is natural log of y equals x. So our example shows this. If we have e to the 2.079 equals 8, the way that we would write that is ln of 8 equals 2.079. And we want to remember and consider that we cannot take the log or natural log of a negative number. So we also need to be aware of that. Let's practice rewriting equations in logarithmic form and exponential form. So we're going to use our facts from the previous slides. So if I think about 5 to the negative 2 equals 1 over 25, I want to write this in log form. So I'm thinking about 5 as my base, log base 5 of 1 over 25 equals negative 2. 5 to the negative 2 equals 1 over 25. So I want to move to the next one. 12 to the second equals 144. And I want to write this in log form. So my base is 12. Log base 12 of 144 equals 2. 12 to the second equals 144. And that's how you can check yourself. So this is something that we definitely want to be comfortable with. Let's now rewrite each equation in exponential form. So if I start with this one, log base 8 of 2 equals 1/3. So I'm thinking about my base as 8. 8 to the 1/3 equals 2. And I can confirm this for myself. So if I think to myself, what is 8 to the 1/3? That's thinking about the cubed root of 8. That's thinking about this. So what is the cubed root of 8? What number multiplied times itself 3 times is 8? And that is going to be 2. So that's like a little check for myself. 2 times 2 times 2 is 8. So that verifies that. And you don't have to take that step, but eventually we will be solving these, and you do want to think about that. For our last one, log base 15 of 1 equals 0. Again, the base is 15. The exponent is 0. 15 to the 0 equals 1, and that does make sense. So just using our properties here, we can build these. Let's take a look at some important properties, specifically inverse properties and one-to-one property. So the first one, log base b of b to x equals x. And our example here, we want to think about this as what number do I raise 10 to in order to get 10 to the third, which 10 to the third is 10 to the third. So that makes sense how that works. For this inverse property, b to the log base b of x equals x. And our example again, what number do I raise 10 to in order to get 100? So we really want to think about how these work and see them in action tomorrow. And our one-to-one property, which is actually very useful, if I have log base b of x equal log base b of y, notice that they have the same base b, then I can say x equals y. And for our example here, both are base 2, so x will equal 10. Let's practice condensing and expanding logarithms. So for our first one, log of 7 plus log of x, notice that no base is written in. Thus, it's assumed base 10, common log. So we're going to use the product property in order to condense this. So what that's saying is log of 7 times x is going to represent log of 7 plus log of 10, and this is because they're both base 10. So I'm going to write this more sophisticated as log of 7x. For this problem, we're going to use the quotient property and the power property. So I first want to illustrate the power property by bringing the 2 that's in front of log base 4 of x to the exponent. So I'm going to write this as log base 4 of x to the second minus log base 4 of 2. So that's one of my first steps here. Now I want to use the quotient property in order to simplify this and condense this even more. So log base 4 of x squared over 2 is going to be how this simplifies. And I want to be very careful with my notation. For the last two, we want to expand each logarithm. So if I think about this, I want to use the quotient property. Eventually, you're going to get more and more comfortable determining which property you're going to be using. So I'm going to think about this as log base 5 of 25 minus log base 5 of x. And here I'm going to assume x cannot equal 0. So this would be the expansion for this problem. And for my last one, log base 4 of 9 times radical x, I'm going to use the power property and the product property. Log base 4 of 9 plus log base 4 of radical x. And I want to take this a step further and think about what radical x means in respect to exponents. And this is when you want to think about your exponent rules. So log base 4 of 9 plus 1/2 log base 4 of x. And when I see radical x, I'm thinking about this as x to the 1/2 power, and then I want to bring that exponent to the front. So this is going to be my final answer for log base 4 of 9 times radical x. And this is how we can condense and expand logarithms. Let's take a look at the change of base formula. Log base b of m equals log of m over log of b. Notice that this uses common log or base 10. For these problems, we are going to use our calculator. And if you notice on your calculator, we have a natural log and a log button. The log button is specifically for base 10. So log base 4 of 7 is going to be log of 7 over log of 4. And we get this from our equation. So I can now use my calculator to type this in and evaluate. Log of 7 divided by log of 4 is going to equal about 1.4036. If I think about log base 81 of 27, I can think about this as log 27 over log 81. And we want to be careful here not to reduce. We can't reduce these by 3. We actually want to type these into our calculator and get a value. So log 27 divided by log 81, both base 10 are common log, is going to equal 3 over 4 or 0.75. So this is how we use the change of base formula, and it is going to be very handy once we get to equations. Let's take a look at some additional problems where we need to first condense. So for the first one, we can use the product property. Since we have base 9, we can say log base 9 of 3x equals 2. So 9 to the second equals 3x. 9 to the second is 81. So again, I'm solving for x here, so I divide both sides by 3, and I get x equals 27. Throughout these problems, I do want to make sure I'm not taking the log of a negative number. So for number 2, ln of 3 plus ln of x equals 4, again, I'm going to use the product property. So ln of 3x equals 4, and when I see an ln, I should be thinking about my base e, which then allows me to say e to the 4th equals 3x. E to the 4th is just a value on my calculator, so we do want to get our calculators out, and we're going to actually figure this out. So e to the 4th is going to equal about 54.598, but I am dividing this value by 3. So before I actually do that, I want to have the most precise answer as possible. So x is going to equal e to the 4th divided by 3. And I can just do this on my calculator, and I get x equals approximately 18.1993. Let's take a look at 2 more. Log base 7 of x minus log base 7 of 2 equals log base 7 of 60. We're going to see the one-to-one property. We're in base 7, so I'm going to write this as log base 7 of x over 2 equals log base 7 of 60. And since I have log base 7, I can then extend this to be x over 2 equals 60. Solve for x, multiply both sides by 2, and I'm going to get x equals 120. For my last problem, using natural log, I see something similar. So again, I'm going to see my quotient rule, ln, and if I want to write base e, I can do that. It's up to you. This is going to be x minus 1 all over 4 equals ln of 8. And since these are both base e, I can then say x minus 1 over 4 equals 8. Multiply both sides by 4 to cancel out that denominator. And I'm going to get x minus 1 equals 32. Add 1 to both sides, so x is going to equal 33. So we can see various problems where we have to first condense and then solve. So keep this in mind as you're thinking about these problems and solving them. After watching today's video on exponential and logarithmic functions, let's look at the essential questions. What is the relationship between exponents and logarithms? When do logarithmic equations have extraneous solutions? What real-world applications illustrate exponential and logarithmic functions? Think about these questions tonight, and we're going to discuss them in more depth as we cover more problems in this unit. After watching today's video, try these. For these problems, rewrite each equation in logarithmic form. For 3 and 4, rewrite each equation in exponential form. For 5 and 6, condense each expression to a single logarithm. For 7 and 8, expand each logarithm. And for 9 through 17, evaluate the following logarithms. Bring these problems in tomorrow and we'll discuss them in more detail. Thanks for joining me in Core Concepts in Algebra 2. See you next time.